What's up everyone, I'm going to be solving a test, test 3, and this test is going to be taken using StatCrunch. So we have StatCrunch here, and the topics covered on this test are sampling distributions, confidence intervals, and hypothesis tests. One of the harder tests in a statistics class. Let's get started. Here we go. So number 1, ages of coronavirus deaths are normally distributed with a given mean and standard deviation. What's the probability that a random death was from a person who was younger than 35 years? So this is just a normal calculation. And notice that it's a random death. It's one person's death from the population of all of the deaths. So it's just a normal calculation. So we can go to StatCrunch. Let's pull this off. Maybe we'll put it over here. And then we'll just go to the normal calculator. So stat, so this is StatCrunch, so stat, calculator, normal, and then we just plug our data in. We have a mean, 54.38. Let's see if I can copy this in. Good, I can. I'll copy this in. Control C, Control V, and then I'm going, says younger than 35, so good, we have the right direction on the inequality. Control C, Control V, press compute. There you have it. Now it says round to the thousandths place, so what I'm going to do is put 0.182. So that's your answer. There you have it. Now, second question is very similar. It does say that it's a mean of a random sample of 40 deaths, so we need a sampling distribution on this one. So we have a sampling distribution that has a specific mean. That's actually, the mean is going to be the same. It's the same as the population mean, but the standard deviation is going to change. You're actually going to divide the standard deviation by the square root of 40. I think the sample size is 40, right? So that, yeah, so the standard deviation changes. We call that the standard error. So that's it. I mean, everything's set up. We're still going younger than 35 years, so we press compute and we get that. Now, here's the tricky thing. Pay very close attention to this answer. There's an E -9 there, and that means this is scientific notation. So basically, there's going to be 8 zeros to the left of this 4. So that means if I round this to the thousandths place, it's basically 0. Or really, it's 0.000 if you want to round to the thousandths place, which is the same thing as 0. So that's the answer on that one. Number 3, different question. According to a survey in a country, 17% of adults do not own a credit card. Suppose a simple random sample of 800 adults is obtained. Would it be unusual for a random sample of 800 adults to result in 205 or more who do not own a credit card? This is probably the hardest question on the test. And let's see, it has to do with the proportion. So it's really it's a similar question to what we just did. It's a sampling distribution question, but it's dealing with the proportion, the sampling distribution of p hat, the proportion. So the mean here of the sampling distribution is 0.17. The standard error is really hard to get. Let's see, how should I get this standard error? Maybe I'll use Desmos. Why not? It's easier to kind of see on Desmos. Let's see, standard error is going to be, actually I can do the square root first. Square root, then put a fraction in. And let's think, it's a standard error, and we know the proportion, so it's going to be 0.17. 1 minus 0.17, see that? Divided by n, which is 800. So that is the standard error. And we have the number right here with a lot of precision. We'll take all of that precision, Control C, go back to StatCrunch, Control V, plug it in. See? So there you have it. And now it says, would it be unusual for a random sample of 800 adults to result in 205 or more? So I'm going to change this to greater than or equal to and put 205 divided by 800. Press compute, and that's the answer. Now, this question wants me to show my work. So basically I would copy paste this whole thing in here. I'm not going to do it right now, but the answer here is basically that. That's the answer. Control C, Control V. But make sure you show your work. I'm not showing my work here, but that's the answer. Now, it doesn't say it rounds to anything, so you're pretty much can put this as the answer. If it wants you to round it, then yeah, you gotta do something else. Maybe put 0.000. That's it for that one, and like I said, make sure you copy this whole thing to show your work, if you're supposed to show your work in StatCrunch. So that's it for number 3. Number 4 says the following is a conceptual question and doesn't require any calculation. What would have a smaller probability, the mean of 40 dogs being more than 60 or the mean of 100 dogs being more than 60? Assume that the mean weight of dogs is some value less than 60. Explain why for full credit. So look, here's the idea. Let's see, how can I draw this? I can't really draw this that easily since I'm using the computer, but I'll explain it instead of drawing it. It's better if I draw it, but I'm going to explain it. Well, basically the sample size is bigger. 100, think about this. For a bigger sample size, 100, or let me point out that there are 2 sample sizes. Let's see, what are the 2 sample sizes? The mean of 40 dogs. So you have one scenario where you only take 40 dogs, right? And you have another scenario where you take 100 dogs. So those are 2 different scenarios. Now, what's the difference? What's the difference between taking 40 dogs and 100 dogs? The difference is when you take a bigger sample size, your sampling distribution is more accurate. It's more condensed. It's really close in. Therefore, your probability of getting a mean greater than 60 will be smaller because your means are going to be closer to 60. Or they're going to be closer to the mean, whatever the mean is. The mean weight of a dog is some value less than 60. Let's imagine that it's 50. Well, for a sample size of 100, all of the means are going to be really close to 50 because the sample size is bigger, so your means, your sample means are really accurate. So they're really close to 50. So the probability of getting, let's see, so let me wait. Yeah, probability of getting 60 or above, getting the mean of 100 dogs to be 60 or above would be smaller. You know what? I should write this down since we're supposed to explain why. So I'm going to say, okay, how about this? The mean of 100 dogs being more than 60 is less likely since the sample means will be closer to the population mean, since the sampling distribution of mean, this is really long, of means, oh, this is complicated writing it like this, of means of sample size 100 is, let me see, how do I want to write this? The mean of 100 dogs being more than 60 is less likely since the sample means will be closer to the population mean. I'm getting too complicated. More accurate. This will make it less likely that a mean will be bigger or larger than 60. So yeah, I was getting too complicated. Let's just leave it like that. That should suffice. The mean of 100 dogs being more than 60 is less likely since the sample means will be closer to the population mean because it's more accurate. I should maybe put that in parentheses. Closer to the population mean, more accurate. This will make it less likely that the mean will be larger than 60. Yeah, I wish I could draw this out. It'd be better if I drew a picture, but we'll just use our words on this one. Okay, that's number 4. Number 5. Find a 90% confidence interval. Round your answer to the nearest tenth. So this one, just plug in this data and find the confidence interval. Well, actually, we're supposed to do this by hand, aren't we? Since we're supposed to show our work on this one. And I want them to do this the long way. So what I'm going to do is, let's see, I want to do this between, now think about it, this is quantitative data. So I'm going to be using the normal distribution. I don't know the population standard deviation, so I'm going to have to rely on the sample standard deviation. So what I'm going to do is first I'm going to get the critical value for this formula for the margin of error. I need the critical value, so I'm going to go to between. I'm going to put 0 and 1 here. This is the critical value, so standardized score. And I'm going to go here and put 0.9, and I get 1.6449. Okay, that's my critical value. And I also need the mean and standard deviation, don't I? I just realized that I need the mean and standard deviation. I think, do I have it somewhere? Because I did this somewhere. Let me see if I have that there it is. So this is number what? This is number 5. So I think I have the mean and standard deviation. Well, I don't really want to plug it in, but for the sake of, yeah, I will. I'll just do it. 3120, so you can see how I get the mean, just in case you didn't know how to get the mean using StatCrunch. I'm going to show you 840, 668, 790, 1762, 3200, 2010, 31, 43, 1228. Let's see, do we get everything? That's 10 values. 1, 2, 4, 6, 8, 10. That's 10 values. So hopefully I plugged all this in. Now I just want to get the mean real quick. So I'm going to go to stat, summary stats, columns, and then just click the variable 1. That's where we put it. All I need is the mean and standard deviation. And that's it. So now I got my data there. So that's going to help me with my calculation. Let me move Desmos over here so I can see that. Oops, let me leave it down here. So watch what I do. I'm going to press enter, and then I'm going to plug into the formula for the lower bound. So I'm going to say lower equals to, and this is what I'm going to do. I'm going to say 1797.1 minus the margin of error. So I have the critical value. Where is it? Here. So I'm going to copy this, Control C. There's my critical value, and I'm doing the mean, so I'm going to do a fraction. So I'm going to say times fraction. I'm going to put the standard deviation, which was where? Where did I put the standard deviation? Somewhere. In StatCrunch, it was somewhere. There it is. 1024. I'm going to Control C that. Control V. I'm going to put the square root of n. The sample size was 10. So I'm going to put 10, and there you go. There's your lower bound. Press enter, and you have your, oh, it's not giving me an answer because I have lower. Control C, Control V. There's my lower bound, 1264. And yeah, what number is this? Number 5. Double check it. Ah. Okay. So I realized that I used the normal calculator instead of the t distribution calculator. I'm glad I checked this, because this value here, 1.645, is actually, I did something wrong. It's wrong. This value here is wrong. I need to use the t calculator because we don't know sigma. Like I said earlier, we don't know sigma. We have to use s. We use it. We estimate sigma with s. Therefore, we're dealing with the t distribution. So I need to close this. I need to go to stat calculator, t distribution, go to between, and then I'm gonna put, what's the sample size? Oh, the degrees of freedom at 9. So then I'm gonna go over here, put 0.9, and then press compute. There you go, 1.8331. Control C. And now the beauty of Desmos is kind of nice. It allows you to just replace stuff like that, and there you go. I'm glad I checked that one. So that is the real answer. So it's a common mistake that people make. They forget to use, they use the incorrect distribution. This is modeled by a t distribution, not a normal distribution. So you have to use the t distribution, right? So I did the t calculator. See that? So then to finish this off, let me find Desmos. Here it is. The lower bound is that. So yeah, and then your upper bound, you just change this to plus, so you can maybe go to the next level, and then Control C, Control V, just change this to plus, however you want to do it. You don't have to go to the next level, but I did just so you can see them both. So this is the lower bound, and this is your upper bound. And that is your answer for question number 5. Now you're going to need to show your work, so you need to kind of copy paste all this stuff in, or put it in however you can. I don't think I can Control C and Control V, can I? Yeah, not really. I'd have to do that in the equation editor. I can do that if I do equation editor and then just say lower equals to and then Control V. I think that'll work. Maybe not. Let's see. If I insert equation, let's see how that looks. Nah, that one didn't work, but it should work. Maybe we just paste it like without the lower. Not working this time. So you're gonna have to figure out how you're gonna put it in for the test. I thought that would work. Maybe if I just copy part of it, Control C, or if I do, let's see, Control V. Oh, I see. I have to make sure I'm in LaTeX mode. Yeah, I don't know. It's a minor issue. We're not talking about that right now. We're talking about how to get the answers. The answers are this and this. These two numbers. This is your lower bound of the confidence interval, and this is your upper bound of the confidence interval, and this is your work. You need to show your work, so this is it. This is the formula for the lower bound and formula for the upper bound. This middle thing right here, or this just what I'm highlighting here, that's the margin of error, and this over here is the point estimate. In this case, it's called X bar. Yeah, X bar, X bar. We're dealing with the mean, so that's X bar, and this is the margin of error right here. This thing in the numerator is the standard deviation, S. Yeah, and this is called the critical value. So yeah, there you have it. Now I'm gonna move on to the next one. That was our confidence interval. True or false? If we want to make a confidence interval more narrow or smaller, we should increase the confidence level. That is false. When you increase the confidence level, the interval actually gets wider because you need to be more confident. So that is false. Number 7, if the critical value for a confidence interval gets bigger, then E gets bigger, smaller, or stays the same. That is bigger because they're directly proportional. The critical value and the margin of error here. This is the critical value. Let's see. This is the critical value. So if this gets bigger, 1.8331, I'll demonstrate that. If I make this to, so look at how big this is called the margin of error, 593. If I make this 2.8, if I increase this critical value, well look, it changed from 593 to 918. See? So increasing this critical value increases the margin of error. I just kind of showed that with Desmos. It makes it bigger if the critical value gets bigger. Number 8, for a 99% confidence interval, check the conditions. Okay, conditions. Okay, the conditions on this one, I think I have this somewhere. I'm gonna do just maybe I'll copy paste this. Might be faster. Ooh. Let me see. Can I copy this? I don't know if I can. Control C. So the first condition, simple random sample. Number 2, I don't know if this will paste. Actually, this won't. So let me just pull this in. Number 2. Okay, here are the conditions. Number 8. Conditions for a confidence interval. What are we doing here? This is as I move this so we can look at the question again. It says a 99% confidence interval, check the conditions. A virologist randomly samples 200 Americans in New York and finds that 24 have COVID-19. This is a proportion because they have 24 and 200. These are not means and standard deviations. This is a proportion. So I need to do the conditions for a proportion. So I have it here. Number 1, simple random sample. Number 2, you have to check that n times p times 1 minus p is greater than 10. Greater than or equal to 10. It is, because it's 21. And then lastly, you have to check independence. So you check that 20 times 200. Why do I put 200 there? Because that's n, the sample size, lowercase n. So 20 times the sample size is 4,000. Now there needs to be more than 4,000 New Yorkers in America, or Americans in New York. Are there more than 4,000 New Yorkers? Yes, there are more than 4,000 New Yorkers. Therefore, the population size is more than 5%. Is greater than 5% of the sample size. In other words, the sample size is less than 5% of the population size. This is a way to check it by multiplying 20 times the sample size and just stating, hey, there's more than 4,000. There are more than 4,000 Americans in New York. A Okay, so that's number 8. We just checked the 3 conditions, 1, 2, and 3. It's difficult. One thing students struggle with is they mix up the conditions for the mean and the proportion. Now what is this? This is the proportion. See, 24/200, that's a proportion. Alright, moving on. Let me move this out of the way. Okay, so number 9 is a confidence interval. 99% confidence interval. And is this the proportion? Yes, it is a proportion. So now this one you can use the normal distribution. If it's the mean and they don't give you a sigma, you have to use the t-distribution. On this one, you can use the normal distribution. So I can get rid of this t-calculator, grab a stat calculator, get a normal calculator, press between, and then just get rid of this and put, let's see, 0.99. This is a 99% confidence interval, so 2.57. There's your critical value. Okay, so you're gonna need to remember formulas. Let me see, can I move this over? Yes, I think I can. Give myself some room. Alright. Now what's going on? You have the p hat. This is a job for Desmos. So what I'm gonna do, let's go to Desmos and put a fraction. So I know the formula. It's 24 divided by 200. That's p hat minus the critical value. And we're using a normal calculator, so be careful, make sure we don't make a mistake. We're using the normal calculator times, and then I'm gonna put square root, and I'm gonna put fraction in here, the standard error here. Now this is a confidence interval, so I'm gonna use p hat. I don't know p, the population proportion. I only know the sample proportion, which is 24/200, right? So Control C, Control V, 1 minus Control V, n parentheses, and then 200 down here. There you have it. That is your lower bound for your confidence interval. And I could just, let's see, can I press enter and go to the next one? What's going on? Why isn't it cooperating and going to the next one for me? Oh, there we go. So then, okay, that's my lower bounds. If I Control C, Control V, and then replace the subtraction sign with a plus sign, I get that, and there are your answers. Now it does say round to 3 decimal places, so I'm gonna just put this, I'm gonna show you my rounded answer. It's equal to 0.06 that's the thousandths place, and then the upper would be equal to 0.179. And now this is showing your work. This question, you have to show your work. So this is your work. This is the formula that you're gonna need for your work, right? So yeah, that's it for that one. And that is your 99% confidence interval. We just found a 99% confidence interval for the proportion of people in New York with COVID-19. Okay, number 10. State the null and alternative hypothesis. That sounds to me like a hypothesis test to find the parameter. And this is so I see a percentage right off the bat, so I guess this is a hypothesis test about the proportion, right? Now, let's see. A recent study tested 650 people and 240 had the virus. Perform a hypothesis test with 0.01 significance to assess whether this represents evidence that the proportion has increased. So 7 months ago it was 33% with the coronavirus, and then a recent study we got that. So by the way, I'm just curious, what is, come on, this is not cooperating again. Why not? There we go. What is, let's see, 240 divided by 650? That's 37%. So that's an increase. That is an increase. But we want it, but that's an increase from that sample. That's only 650 people. But several months ago it was 33%. That's for the whole population. So, but now we only have a sample of 650 people. So we want to know, hey, from that sample, is that showing an increase in the percentage of people with the coronavirus? And these numbers are all made up, so I don't trust the accuracy of these numbers. I don't know if it's 33% or 37%. I made these numbers up. 650 and 240 I made up. So let's see. State the null and alternative. I'm gonna say, do I really want to put some symbolism here. Let's see. H subscript 0. And now they don't like colon. There's no way to put a colon. That's annoying. So what I'm going to do is, I forgot you can't put a colon, huh? So let me just insert that equation. And I'm going to do what a student told me. Just press, get a colon, press copy, Control C. One of my students came up with this brilliant idea. And I'm going to come in here and I'm going to press Control V. I got a colon now. Now, I mean, I just want P equals to 0.33. That's the null hypothesis. And then the alternative hypothesis is if I press enter and then just Control C, Control V using control keys. Now I press this, I go back into the equation editor and I change this 0 to a 1. This is my alternative hypothesis. And then we change this to what are they trying to show? An increase, I believe. So there you have it. It's your null and alternative, and make sure you define your parameters because the question says state the null and alternative hypothesis symbolically and define the parameter. It says increased, right? Yeah, increased. That's why I made this greater than. So then I'm going to say where P is what? The proportion of, should I say Americans? Does it say where? So I'm just going to say people because it doesn't specify a specific country or anything. So I'm just going to be as specific as the question, where P is the proportion of people with coronavirus today. I'm gonna say that's an important word, that word today, because we are comparing several months ago with today. So you can say currently or today, and I'm gonna say, I forgot something, proportion of people with coronavirus today, or in the population today. So this is a population proportion, that P stands for the population proportion. So I like saying in the population. So there you have it. That's how you answer this question, number 10. All right, moving on. Let's continue this question by finding what? The test statistic and p-value. Show all your work. So show all your work, okay? So how do we show our work on this one? Round everything to the 4th decimal place. How do we do this? Well, let's see what's going on. We have to find the test statistic. So what's the formula for the test statistic? This is dealing with the proportions. So let me see if I remember this. It's let me put a fraction somewhere, and I'm gonna put the test statistic is p hat minus p. So what's p hat? 240 over 650 is p hat. So minus 0.33, that's p, divided by the standard error. Now for the standard error, am I going to use p hat or p? Since this is a hypothesis test, so for the p in here, there's a p in this formula for the standard error. It's p1, how come it didn't show p? p1 minus p over n. That's the formula, but sometimes it's p hat. For this question, it's p because it's the population. This is the, or let me take that back. For this, we're going to use p because we're doing a hypothesis test where we assume that p is 0.33. So we are assuming that the proportion is 0.33. That is our null hypothesis. So we're assuming it's true, so we use it. So 0.33, 1 minus 0.33. It's tricky because sometimes you use p and sometimes you use p hat. So sometimes I use this if I'm doing a confidence interval. That's p hat. But if I'm doing a hypothesis test, I have to use p. And then n is 650. So there you have it. That's your test statistic. And you're going to have to show your work. So this is your work. You could say, so look, the number is there. Let me go down to another level and just Control C. So if I was to show my work, I'd say this is a test statistic. It's Z sub 0. Oh, can I do a subscript here or no? I don't think so. So I'll just say Z. Oh, whoa, it's a subscript. Oh, look at that. My goodness. Z0 equals to, I just used the shortcut key for Microsoft Word to get a subscript, and it works on decimals. Amazing. Yeah, okay, so, and then, okay, whatever. Now I'm going to say Control C, Control V, and there you go. Maybe put the equal sign here. 2.1 0.27. What are we supposed to round to? 4 decimal places? 1271. There you have it. That's a beautiful. That's it. That's your answer. Take a picture of that and insert it. There. That's it. That's perfect for your test statistic. Okay. And then for your p-value, notice it's giving you an error because obviously this is the answer's up here. This is kind of for me to show my work. Wow, this is nice to show your work like that. Now for the p-value. What's going on with the p-value? We have to look here. Okay, it's a right-tailed test. So, what happened? It's a right-tailed test. So I'm gonna go to the normal calculator and I'm gonna plug in my mean of 0.33 and my standard error of what? Let me go to decimals and get the standard error. I don't know if I got it, but this is the standard error right here. Control C. There it is. That's your standard error. Control C, Control V. Okay. Everything okay. We got the mean. We got the standard error. Make sure everything's correct. And then now what are we doing? We're going to do standard and then go greater than, I believe, since it's a right-tailed test. And our test statistic is positive. So Control C, Control V. Press enter and you get 0. 0, is that right? Let me think. What seems right? Oh yeah. Oh, nice. This is not right, and I know why. Do you guys know why? Did you guys see the mistake here? What went wrong here? Do you see what went wrong? Just to give you a second to see what went wrong. What did I do wrong? I made a mistake. Can you guys see it? Well, the mistake is that the mean should be 0 and 1 since I'm using a standardized test statistic. I could have done this in a shortcut fashion where I delete this and I just use p hat here. This is kind of faster. I could just press Control C, Control V, press compute. Oh no, it did it like that. How come it did that? Oh, let me just take this then. Control C, Control V. I could have done it this way. It's a lot faster, and just that's my p-value. Remember this number, 0.01670564. Remember that number, 0.01. In fact, since you can't, maybe you won't remember it, I'm just gonna put it here. Okay, so look at it. I did it that way by using a normal distribution, but I'm gonna use a standard normal distribution to make this 0 and 1. Why is that 0.0? Make that 0 and 1, and then I'm gonna do it where I'm gonna get the z-score, the standardized test statistic. This 2.1, right? This is a Control C, Control V, press compute now, and look at the numbers. They're exactly the same. See that? Control C, I'll put them right below each other. They're exactly the same. So that's the p-value. Now to show your work for the p-value, you just need to insert a picture of this right here, what I'm highlighting right down here. Just insert that, and that's your work for your p-value. You just use StatCrunch and you got the answer from the p-value. And then for your test statistic, because it says show all work, right? So for the test statistic, this is your work. So 2.1271, that's your test statistic. And this is your p-value. Okay, next one. Number 12, interpret the p-value. Okay, the probability, there's two. So I'll do the sentence interpretation. Some people did it symbolically. I was pretty impressed by them. But the probability of getting a test statistic as big, as extreme, or more extreme than 2.127 excuse me 1, given that p equals to 0.23 is 0.0167. There you go. That's the interpretation. I saw some people do this. Probability of getting a test statistic as extreme and it was pretty cool. Given that p equals to 0.33 equals to 0.1001. It's less writing if you write an answer like this. Oh, I got something in my throat. It's less writing. Excuse me. So some people did that. The symbolic p-value interpretation or the sentence. Okay. Moving on to number 13. State your conclusion. The conclusion is, oh well, I don't know, what was our p-value? It was 0.01, 67, and the significance level 0.01. So are we under the significance level? Or is it? Let's see. No, we're not. Tricky, because this is a small p-value, but the significance level is really tight. So we fail. We fail to reject H naught since the p-value is greater. Oh, I like doing like since p-value is greater than 0.01. And okay, that's your technical conclusion. Non-technical conclusion. There's insufficient evidence, I can't spell, to conclude that, and then whatever the alternative, whatever it was, let's see, what the proportion, the proportion has increased. There you go, just copy that. The proportion has increased. Well, I mean, I could get into more detail here, I should. The proportion what? Of people with the coronavirus? The coronavirus has increased. Insufficient evidence to show that the proportion of people with the coronavirus has increased. There you have it. That's the conclusion. Number 14. The sociologist is correct in thinking that the percentage is different. No, he's not correct, because we just showed there's insufficient evidence to conclude that the proportion of people with the coronavirus has increased. In other words, it's still the same. So has it changed? Is it different? Nope, it's not different. Okay, got it? So this is a continuation of the last question. It's just saying, it's like just a knowledge check on making sure you knew what your conclusion was, just asking it in a different way. And is the sociologist correct in thinking that the percentage is different today? No, they're not, because like I said, there was insufficient evidence to conclude that it increased. Okay, so moving on, number 15. Check the condition to do a hypothesis test of whether or not women are getting taller. Now, I don't see any percentages here. Taller, that is a numerical variable, height. So this is the conditions here are different. I think I have the conditions somewhere. Let me see. I checked this somewhere. Where is it? Where is it? What number is this? 15, 15. Let me grab these to save time, so I don't have to type this. Okay, Control V. Okay, there's the conditions. Number 1, simple random sample. Number 2, n is greater than or equal to 30. So the sampling distribution is normal, right? N is greater than 30. That is a condition. Notice what is n in this question? It's 57. 57 women. So look, it says, I didn't read it, in 1990, the mean height of women 20 years of age or older was 62.5 inches. Based on data obtained from the Centers for Disease Control, suppose that a random sample of 57 women who are 20 years of age or older today results in a mean height of 62.8 inches and standard deviation of 1.08 inches. Check the condition to do a hypothesis test of whether or not women are getting taller. Alright, so what's going on in this question? Well, the thing is that in 1990, the height was 62.5 inches, right? That's the thing. In 1990, women were 62.5 inches. Now, the thing is that today, where is it? Does it say today? Yeah, today. So we're comparing today versus 1990. So today, we got a taller sample mean. A taller sample mean, right? 62.5 versus 62.8. Okay, so let's check if this is meaningful or statistically significant. So we just checked the conditions here. Number 2 is to ensure that the sampling distribution is normal. That's why you check that the sample size is greater than or equal to 30, or the population is normal from which it's sampled. But sample size was 57, so we're in the case where n is greater than or equal to 30. Therefore, the heights of women do not need to be normally distributed, because notice it is not stated in this question that heights of women are normally distributed. So that's the second condition. The third condition is that the independence, basically independence. To check independence of sampling, you just check that 20 times n, which is 57, which equals 1140, So you just make a statement that there are more than 1140 in the population. What's the population? Women that are 20 years of age or older. So there are more than that many women 20 years of age or older. Okay, we checked the conditions for this question for the hypothesis test of the mean. Remember, I told you it's tricky. Some people confuse the conditions, right? Notice that the condition is there's no n times p times 1 minus p, right? Greater than or equal to 10. Notice that that condition is not in this question because there is no proportion. There's only the mean. Alright, so we get rid of that. That is not needed in this question. So 16, state the null and alternative hypothesis. Alright, what's going on? What's the null? What's the null? Okay, so 62.5, right? That's the null. Okay, let me do this way. H at, let me press Control V. I do not have the colon there anymore, so let me insert that and just press colon. Control X to get rid of that. Click this. I do not like this that I have to do that, but anyways, we do. Let me go back to the left, and can I put a subscript anywhere? Will it let me put us? There we go. Subscript 0. There we go. So mu, we do have a Greek letter. That's one thing I like right here in Greek. So mu is here equals to, what was it? 62.5, I think. And that's it. There's your null hypothesis using the Greek letter mu for the mean. Insert, and then I think it's 62.5. Yes. So then the alternative, Control C, Control V. Oh yeah, I have to click here to go in there. Change this 0 to 1 for the alternative, and what is it? Is this greater than 2? Or is this a two-tailed test? What is it? Where is it? Are women getting taller? Oh, another two-tail, another right-tailed test. Okay, fine. Where mu is the mean height of women 20 years of, I'm reading the top sentence, 20 years of age or older. Mu is the mean height of women 20 years of age or older in, is there a specific town, state, country? Doesn't say, so then I'm not going to say then either. I'm just going to say in the population today. Because remember, we're comparing today with 1990. Where does it, how do we know we're comparing today? Because it says today, right? Alright, cool. So we have the null and alternative hypothesis, and we defined the parameter, right? Define the parameter. Alright, next one is to continue that and define the test statistic and p-value, and we're going to round to the 4 decimal places. Alright, test statistic and p-value, test statistic and p-value. What's a test statistic? It's, how are we going to do this? We're dealing with the mean, so I'm going to use t, right? Don't make the same mistake I made last time where I think I used the normal. I used let's see, calculator, stat, calculator. I use normal, but I'm supposed to use the t-distribution because sigma is unknown. We do have a standard deviation here, but what is that standard deviation? Is that the population standard deviation or the sample standard deviation? That's the sample. Why is that a sample? Because it's a random sample of 57 women. These two values, this 62.8 and this 1.08, they refer to those 57 women. So I'm going to go back to the t calculator to find my critical value. But do I need a critical value here? Let me think. I don't think I need a critical value. I'm doing a hypothesis test, so I don't need the t calculator after all. I don't think I need it, because what do I need for the test statistic? All I need is, let me think, x bar minus mu divided by s over square root of n, right? I need something different here. So what I'll do, what will I do? Yeah, I think I can go straight to decimals. I don't need a critical value. Okay, so watch. How do I do this? How do I get my test statistic? In the following way. I'm going to call it t sub 0. Why did it do that? Interesting. T sub 0 equals to, And then for my test statistic, I'll put x bar. What's x bar? Where is x bar? And I need a fraction. I'm trying to remember the formula. I need a fraction. What's x bar? 62.8. 62.8 minus 62.5 divided by s over square root of n. So what's s? 1.08. What is n? Where's the square root? Right here, and n is 57. So there you have it. That's your test statistic. Wow, it's actually calculating it for us, even though we have this t equal here. Wow, that's interesting. Interesting. Let me press enter. Just double check that. Control C, Control V. Wow, cool. It did that for us. And I need to round that to 4 decimal places, so 2.0972. That is rounded to 4 decimal places. So there you go. This is your answer right here. Copy that and paste it in. That's it. That's for your test statistic. Now to show your work for your p-value, you're gonna have to use, that's when we have to use the t calculator and not the normal calculator. So let me move this to the left, and I'm gonna go to calculator t. Why am I using a t calculator? Because this is modeled by a t distribution. We don't know sigma. We're using s. 1.08 is s. So we're modeling with a t distribution. So how do I find the p-value? How do I do it? I need to figure out if I'm going, well, it's standard. I don't think it's it's a greater than test. It's a right tilde test. So I'm going to choose greater than. My degrees of freedom are 56. That is my n minus 1, and then this is it. This is all I do is I grab this, Control C, Control V, and there you go. That's it. So there is your p-value right there. So this is your work for the p-value. This thing here. Just take a snippet of this, take a snapshot on your computer of this, and insert it. And that's it. 0.0203 rounded. I should actually show what the rounded answer is, huh? So Control C, p-value. I'll make sure I round it. 0.0203. That is the correct rounded answer to 4 decimal places for the p-value. And the test statistic, and of course I want you to insert this though. Don't just put this, but show your work and insert this whole thing. Oh, you know what? That's kind of lame that some people might not round it if they insert this, but that's okay. Technically, you should insert this thing and then also say this, so that you round correctly. All right, cool. So did we do everything? I think so. We got the test statistic and the p-value. We used the t distribution. Everything looks good. Moving on to number 18 is to state the technical and non-technical conclusions. So let me go back up and see. Okay, there's the p-value. It's less than 0.05. So I'm going to reject the null. Yes, so 0.05. Okay, so I'm going to reject H not since p-value is less than 0.05, and then I'm going to say there's sufficient evidence. Whenever you reject, there's sufficient evidence. When you fail to reject, there's insufficient evidence. It's easy, as long as you're always talking about the alternative in your conclusion here. There's sufficient evidence to there's sufficient evidence to conclude that, and then now what are we going to conclude? What is our conclusion? Are women getting taller? That women are getting taller, right? Control C, that women, oh, I think I did that wrong. I think I just, women, oh, look at that, how convenient. That women are getting taller. To conclude that women are getting taller. Yeah, we can conclude that because we rejected the null hypothesis. There is statistically significant evidence. Yeah, there's sufficient evidence to conclude that women are getting taller, which is kind of interesting because you wouldn't think so, right? Because 62.8 versus 62.5, it's kind of close. But why is it? Because what's happening is our sample size is 57. That's condensing the sampling distribution, making it really, really tight. So what's the square root of 57? It's almost the square root of, well, square root of 49 is 7, so it's a number greater than 7. So if you divide 1 by 7, that means your standard error is going to be whatever that is. It's pretty small. So then that makes it that 62.5 is, what's that difference? 0.3? Well, the standard error is probably going to be like 0.14 or something, right? Like double that. If you double 0.15, you get 0.3. So that means that 62.8 is more than 2 standard errors away from 62.5. So sorry if I lost some people there, but that's kind of like, just because these two numbers are really close to each other doesn't mean that there hasn't been a big increase, because in this case there has been a big increase. Women are getting taller. It may not be practical significance, but it's statistical significance. You may be like, well, it's not too practical that women didn't get that much taller. But anyways, 19 and 20 almost done. Yay. So 19, describe a type 1 error. Type 1 error is rejecting a true null hypothesis. So you're going to say, but if you just say reject a true null hypothesis, then you're not going to get correct. You're not going to get marked correct. You're actually only going to get 0.22 on this as your credit. This is 0.5, right? So don't just say reject a true null hypothesis, right? You have to explain it how, in context. So what does it mean to reject a true null hypothesis? Well, that means stating that women are getting taller, can't spell, when they aren't. Stating women are getting taller when they aren't, because the null hypothesis is that they're not getting taller. So we are rejecting that they're not getting taller. That is what it means to make a type 1 error. This is all hypothetical. It has no connection to your conclusion, right? Our conclusion was that women are getting taller. That was our conclusion. The type 1 error is all hypothetical. It doesn't have any connection to your sample data. It's theoretical. It's like it's explaining a situation, but it's not a situation that occurred. So it's just stating that women are getting taller when they aren't. Okay? There you go. That's the type 1 error. And last question, true or false? Given a specific sample and a null hypothesis, it is easier to reject a two-tailed hypothesis than a one-tailed. Easier. No, that is false. For a two-tailed hypothesis, you're doubling the p-value. You have two different shaded areas, one on the left, one on the right. So imagine this picture right here. This is a one-tailed test. There's only one shaded area. That's the p-value. So that's low. Well, guess what? If it's two-tailed, I double it. So it's doubling this. So this is 0.02. Well, a two-tailed test would be 0.04. So it makes it harder. So basically, is it easier to reject a two-tailed hypothesis? No, it's not easier. It's actually twice as hard. Your data needs to be twice as good, twice as, right? So that's why the answer is false here, because you're doubling the probability. You need to understand the idea of a two-tailed test is that there's two tails. So the p-value is doubled. And when the p-value gets bigger, you have less evidence to reject the null hypothesis. And with that, ladies and gentlemen, I bid you adieu.